All right, welcome back. Today, today we will talk about surface energy for solid. All right. So, in solid, we only use surface energy concept. We forget about surface tension. This is because for liquid, surface energy equals surface tension. For liquid, but it is not for solid. This is because anisotropic property of solid. So back in liquid, they are same because liquid molecules are free to move. Thus, liquid is isotropic. But for solid, different plane has different surface. Different surface has have different crystal structure. As you already learned from crystallography. Okay? Because of this property, of course, surface energy of 100 will be different from surface energy of 111, and it will be different from surface energy of 110. Let's say for FCC or for any kind of structure that is not isotropic. Okay? So in solid, we only use the term in solid. This is very important. Solid, we only use the term surface energy. Surface energy, which is gamma, and unit is still Newton per meter. Okay? Now we are going to talk about how we are going to calculate the surface energy for any crystallographic plane that can be either 100, 111, etc. Okay? Now first we have to think about, let's say there is this plane. This is the surface, right? No, so we want to cut here and we want to make a new surface. Let's say this is FCC crystal, and we will cut from here to get this kind of structure. Now, as you already learned, in top view it looks like this, right? In bottom view it will be sitting on top of this four. So this is, let's call it A, B, A, then this is A, this is B, right? So you want to make B. This will be your new surface. Then we have to break the bond with this knife. Let's call it a knife. Okay? Then it will look like something like this. Just to help you with the visualization. Then it will look like this. We don't have to draw the bottom 5 atoms because we don't need it here, then it will be like, so this one will be connected to all four of these, right? And we have to use a scissor or a knife to cut all these four bonding, and same logic for every atoms in this surface. Think of this as a continuous surface like this, and this is just a unit cell, so it will be periodic repeating arrangement, right? Then we have to cut all these bondings, all of them. So our basic strategy is just to analyze this unit cell, then we can just simply multiply so we can get the whole surface energy, right? And the basic strategy would be, so gamma will be, by definition, is energy per area, right? Then the energy it takes to break all the bondings needed to get the surface normalized by area. So we just need to get this and the area, and this is easy because you can calculate the area like A0, right? But how are we going to get this part, right? Then here comes binding energy concept. So the original definition for binding energy is the minimum energy required to get one atom out of bondings. We will just use this concept. We use epsilon as the sign. All right? Then what is sublimation energy? We use enthalpy of sublimation energy like this, which is equal to epsilon. So let's say this is a BCC crystal like this. So basically it's sublimation energy. All right, let's first start with definition. Is to break all the bondings, the energy to break all the bondings in solid. That's sublimation energy, very easy. This is BCC. Now it will have 8 bonding like this. And sublimation energy is the energy it takes to break all these 8 bondings. That's sublimation energy. So we already talked about epsilon, which is binding energy. This is just the energy of single bond here. All right? Then delta HS equals to half Z and A epsilon. Z is coordination number. Na Avogadro's number. Avogadro number. And what is this half? Why? Why do we need it? So, of course, if you think about it, here Z equals to 8. And you might think HS should equal to 8 times Na times epsilon. So, because there are 8 bondings, of course, the molar enthalpy should equal to 8 epsilon times Na, because there are 8 bondings per unit square. You may think of it like this, but we have to divide it by 2 because we don't want to count twice. Because atoms share a bonding. 2 atoms would share one bonding. This is where where divide by 2 comes from. You can think of it like this. So this has nothing to do with crystal structure or anything like that. It's just simply because 2 atoms share one bonding. So let's say there are this kind of structures bonded like one-dimensionally, and you want to cut all these bondings. Then you just have to cut once for one atom. Here, note that here is shorter because this is the end of, so here is the surface, so there is no atom here. So this is just electrons that are dangling. Then for this atom you cut once, right? Once. Then it will be new atoms like this. And for this new atom you also only cut once. So even if there are 2 bonding per electron, so Z equals to 2, you divide it by 2, then you only end up cutting 1 bond per atom. Same logic goes for this BCC. So let me prove it to you. Let me prove that this half divide by 2 has nothing to do with crystal structure. So it works for any kind of crystal structure, including BCC, FCC, or simple cubic. That too is only because 2 atoms will share one bonding. Only because of that. I'll prove it to you. So we will draw BCC crystal like this, and it is bonded like this. So when you count how many bonds you need to cut to sublimate this 4x4 structure, then you need to cut 8 bonding per unit cell, right? And you have 64 bonding per 8 unit cells. This is how many bondings you need to cut. And there are 2 atoms per unit cell. And there are 8 unit cells, so 16 atoms per 8 unit cell. Then 60 bondings per 8 divide by 60 UC. 16 atoms per 8 UC. Here like this, then it will be 4 bondings per atom, right? But Z equals to 8, so we proved that you need this 2 divided by 2 to not count twice, okay? Because if you count Z equals to 2, then you have to cut here and here twice, but we already said you just cut once, okay? So that's how you you get the binding energy. Epsilon equals 2. So sublimation energy equals to C epsilon Na divided by 2. Then epsilon will be equal to 2 HS CNA. For all most solid, this is given as data. So this is how you calculate how much energy you need to cut one bonding. That is binding energy. This is how you calculate binding energy. Sorry. You just Google this HS online, then you can get this, right? Then we can finally calculate how much energy you need to cut this, like this. You cut, then you know number of bondings, then you just need to know, you already calculate epsilon. If you know how many bondings you need to cut to get this new surface, then you just have to multiply that by energy of single bonding. We already know how to calculate this. Now next lecture, we'll see how this number of bondings is different for different crystallographic plane. We'll see how it's different, and it will result in different surface energy. That's what we're gonna do in the next lecture. Thank you.